going to talk about closed sets, open sets, and limit points. And in particular, a lot of you ask questions about how to visualize limit points. So we're going to start with that. So I have a picture here of a number line of a limit point, and the definition just says that this thing L is a limit point if for any epsilon neighborhood around it, whenever you draw, see, I need to get my pencil back here. Whenever you draw any sort of an open interval around it, maybe L plus epsilon, L minus epsilon there, you should always be able to find some element of your set A within it. So if that's really what a limit point means. But wait a second, maybe you want a smaller epsilon. Well, let me stop. This is the basic idea. No matter how small you make this interval, you always be able to find some element A of your big set A. And you can continue this process. If you wanted to make an even smaller interval, like that, well, what you do is you'd find a different point, maybe A prime that's in A. Okay, you want to get in closer? You can do that. The only catch is that if L belongs to A, then L doesn't count. You don't get to use that as your point. Because that's really too easy. Otherwise, then every point of a set is a limit point. So that's completely boring. And just a couple pictures of many typical limit points. These aren't the only ones. Well, I don't know if these are the only ones or not. So here you have a number line. Let me draw in red kind of a set. So the set's going to contain an interval. There. Maybe it's also going to contain a couple points here, and maybe the bunch of tiny little dots there. They get closer and closer to this right here, but those are just dots. In this, I would say that there are three limit points. L1, this is kind of a typical one where there are actually four types of limit points. L1, I'll write it down so I don't forget. Four types in this picture. L1 is just kind of the end of an interval, a closed end of the interval. Because if you draw any sort of epsilon ball around it, there are an infinite number of things to the right of it that are in red. So a second limit point would be the other end of the interval. Now these are different types of limit points because this L1 is in the set and L2 is not because it's an open circle. A third limit point would be over here, L3, where I have this sequence of dots that's kind of getting closer and closer to here, and if they're kind of compactifying, then that would be a limit point. A classical example here would be 0 is a limit point for this set, 1 over n, such that n belongs to the natural numbers. Right? So you have all these 1 over n's getting really close to 0, but they don't actually hit it. But any sort of epsilon ball I draw around 0, you're going to include one of these 1 over n's. A fourth type of limit point would be just something right in the middle, right? There's stuff that surrounds it on both sides. It's pretty standard. So basically, a set is closed if it has to contain all these L1, L2, L3, L4 types of limit points. And there might be other types of limit points that I'm not imagining. I mean, certainly I can't really visualize the Cantor set completely, so I don't really know what's going on there. But that might have different sorts of limit points too, which is why we need a definition, can't completely rely on pictures. But this is the standard picture. An open set. Let me draw a 2D representation of an open set first. A set is open if whenever you pick a point in here, what you can do is you can draw a little epsilon ball around it. That's completely contained within the set. You can't go over at all. So in this example, it's open because if you pick any point in here, you can draw a little epsilon ball and it's going to stay completely inside. You can't overlap your epsilon ball outside.